Hello everyone. So today let's solve the problem number 310, minimum height trees, right? So what the question states here, given a tree of n nodes. So we have been given a tree of n nodes, 0 to n minus 1 and n minus 1 undirected nodes actually. Yeah. So what we need to do here, we have to choose a route to minimize the tree height, nothing but longest path from the root to the leaf. Yep. So we have to return all the root labels. Yeah. So we have to return all the root labels actually 0, 1, 2, 3 here, right? So and the leaf here, see this one, 2, 3, 0, 3, 0, 2 they have mentioned here, right? So we have to return all the root labels that produce the minimum height, nothing but MH, this one, right? Minimum height tree is nothing but MHTs actually. The graph approach, basically, let's go with a graph approach here. So what we'll be doing here, let's find the tree centers by iteratively trimming until less than or equal to nodes remain actually. So let's discuss this one by considering the example one, so that you can just go with the same for the example two as well, right? So let me show you for the example one. So the approach, one second. So we'll be going with a topological sorting. Just remember, we will be going with a topological sorting. Just give here topological sorting approach, right? So let's discuss the same thing by considering, let's consider, sorry, yeah, let's consider the example one for the approach actually. Let's consider the same example here, this one. Yep. So we have n equals 4 here, right? So n we have been given 4, right? Edges we have been given 1, 0, 1, 2 as well as the 1, 3. 1, 2, this one 1, 0, 1, 2 as well as the 1, 3, right? So they have shown you the diagram as well here. 0, 1, 2, 3, right? And this one edges for us, they have given edges 1, 0, 1, 2, and 1, 3, and we have been given 4 actually. 4 in the sense we have 4 this thing, what do we call nodes actually, 0, 1, 2, 3 here, right? So first what we'll do, we'll build the adjacency lists here, right? So we'll build the adjacency lists and degrees basically. Node 1 here, if you observe, node 1 connects to 0, 2 as well as the 3. 0, 2 as well as the 3. So for the node 1, we have the degree 3. For the node 1, we have the degree 3. Node 0, 2, and 3 each are having the degree 1. They are the leaves, right? So each they are having the degree 1 here. They are connected to one node 1, right? So this one I can write it in this way, 0, 1, 2, 1 as well as 3, 1. Yep. So this is fine. Next, what we'll do, the second step. So this is the first step. Yeah, this is the first step. Second step here. So we have to initialize the leaves, right? So let's initialize the leaves. Nothing but leaves here are 0, 2, and 3 respectively, right? So one is the root actually, main one. Yep. So here what happens? Let's initialize the leaves 0, 2, 3, right? So let's remove all the current leaves simultaneously, meaning we will be decrementing the degree of their neighbor 1 by 3 actually. So degree of 1 will be equivalent to the 0. After removal, these things, degree of 1 will be actually 0. Degree of 1 will be 0. Now degree of 1 will be 0, right? So this is fine. So after trimming leaves, we have the remaining nodes, nothing but after trimming leaves. So this one, we have removed this node, and this node. Right now, the degree of 1 is 0, and we are left with only one node, nothing but 1. After trimming the leaves, actually, so when we have removed this one, we are left with only one node, nothing but 1. Yeah. So this is less than or equivalent to the 2, right? So this is equivalent. This is less than or equivalent to the 2, right? So centers we can just consider this one. Centers is 1. Centers we can just consider this one 1. Yep. So which are the MHT roots actually? Which are the MHT roots in the sense minimum height trees root actually, right? So which are the MHT roots? So the trimming process generalizes basically in the sense we repeatedly remove leaves layer by layer until one or two nodes remain actually. Right. First, we will remove this one 0, then we will remove this one 2 as well as the 3 respectively. Right. So this we will, so that we'll be left with 1 actually, which is the center of the node. So this one, this particular one, we will be out this one. We will return this one as the output. Right. So this is how we will be making use of the topological sorting. Yeah. So this one will be returning this one as the output. So the output that we got here is 1, which is equivalent to the output that they have mentioned for the example 1 within the question. Right. So let me delete this one. Yep. 1 within the question. See here. This one. Yeah. So our approach works absolutely correct here. So as we're completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part. So what will be the time complexity here? The time complexity would lead to big of n, and the space complexity would lead to big of n as well. Yep. So the time complexity would lead to big of n because each node and each edge is processed only a constant number of times during the adjacency construction and leaf trimming. So overall time complexity would lead to big of n. So what would be the space complexity here? Space complexity would lead to big of n as well due to the adjacency lists. We'll be making use of the adjacency lists as well as the degree array, and we'll be going with a queue. So basically, topological sorting, we will be making use of the queue itself if you know the algorithm, right? So we will be going with a queue, meaning so we will be making use of the BFS. Basically, the BFS uses queue, right? If you know the topological sorting algo, right? Kahan's algorithm. So and Q together use basically linear space. So overall space complexity would lead to big of n. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n and big of n respectively. Now, as we are completely familiar with the approach as well as the complexities part, we are good to write the code. Let's start writing the code. Yep. So the first part here would be, let's go with a edge case. If single node tree, then that node itself is the root of the only MHT actually, minimum height tree actually, that we know actually. If n equals 1, then let's create the list with a single element 0 and let's return. Yeah. So I'll just do here list of integer. So this is fine. Let me go with the resulting variable res. So this one will be new array list. So this is fine. Yep. So the next one is let's add, what do we add? 0 to the result. And we are just adding the only node, right? So next, what shall we do? Let's return the result. Yep. So let's return the result. So I'll just come out of this one entirely. Now let's build the adjacency list, right? So array list of integer of size n in simple terms, right? So I'll just go with the list of integer. So this is fine. Let me go with the array adjacency. So this one will be new array list. And yep. So this is fine. The next part would be let's initialize each list. In the sense, let's go with the for loop here. So this one will be int I equals 0, I less than n. So this will be I plus plus. Yeah. So I'll just go with the adjacency of I. Let me assign this one to the new. So this one array list. So this is fine. Yeah. Initialize each list. Yeah. So next, let's do one thing. Let's go with the degree array to track the number of neighbors. Nothing but it is useful to find the leaves. Yep. So I'll just go with here in degree equals new int of n. Yep. So next, what we'll be doing, let's fill the adjacency list and degrees from the edges. So let's go with the for loop here. So this one will be int e of edges. So this is fine. Yeah. So within the for loop, so I'll just go with int u equals e of 0. Yeah. So this is one endpoint, and the other endpoint would be v actually. Yep. So this one, let's consider e of 1 respectively. Yep. So this is fine. The next step is we have to add v to use adjacency list, and we have to add u to v's adjacency list, vice versa, right? So let me add that one quickly. So this one will be u dot add of v, and the same thing, similar thing. Sorry, let me copy this line. Let me paste it over here. Instead of u, let me change this one to v, and instead of v, let me change this one to u actually. Fine. Next, let me do one thing. Let's increment the degree of u and v respectively. So I'll just go with degree of u plus plus and degree of v plus plus. Yeah, this is fine, man. Now let's do one thing. I'll just come out of this one for loop. Let's initialize the queue with the current leaves, nothing but degree equals 1. So I'll just go with the array deq of integer. So this is fine. Let me make this one capital I, or else we'll be getting the error. Yep, I'll just go with the variable name leaves here. New array DQ. So this is fine as well. The next part would be, let's go with a simple for loop man. So this one int I equals 0, I less than n. Let me increment the I. So this is fine. Next, if uh, degree of I, if it is equivalent to 1, then leaves dot add of 1. Sorry, did I give 1? So this is I actually. So this is fine. We are just pushing the leaf nodes here, right? So this is fine. The next step would be we have to trim the leaves level by level until remaining nodes are less than or equal to 2. Basically, we'll be going with a Kahn's algorithm or topological sorting here. So basically, what shall I do here? Hmm, how can we have to trim the leaves level by level, that I know, until remaining nodes less than or equal to 2. So let's do one thing. I'll just consider here variable name remaining, and let me initialize this one to the n. So let me write simple while loop, and let me copy this remaining. Actually, I don't want to type this one again and again. While remaining is greater than 2, then what we'll do, int, let me go with leaves count actually. Let me go with actually leaves dot size actually. Yep, so this is fine. So this is nothing but number of leaves at current layer. Now let me go with remaining actually. Remaining equals remaining minus leaves count. Yeah. This one, copy this one and paste it over. This is fine. Next, let's move on with a for loop. So this one int I equals 0. I less than again leaves count. So let me increment the I. So within the for loop, let's do one thing. Int leaf equals. So this one will be leaves dot remove. So we are just getting a leaf here. So the next step would be we have to decrement the degree of all the neighbors, meaning it should be exactly one neighbor for a leaf, right? So let's go with one more for loop actually. For int individual neighbor nei of adjacency here, this one of leaf actually. This is also fair. Uh, Within the for loop, let me go with degree of individual neighbor. So we have to decrement this one. This is fine, man. We are just removing the connection to the leaf. Next, let's go with a simple if condition here, meaning neighbor, if neighbor become a leaf, right? So I'll just give here if degree of neighbor, if it is exactly equivalent to the 1, then we have to schedule it for the next round, right? So just give me a second here. So here, if the neighbor became a leaf, then we have to schedule it for the next round, right? So I'll just go with here leaves dot add of neighbor, right? So this is fine. So here, one thing, so this is optional actually. We can clear the adjacency list of the leaf to free the memory. It is not required, but if you can do that one, you can do, right? So you can just give adjacent this one adj of leaf dot clear. That one basically you can do, but that's not necessary. I'll just go with this part directly. So let me come here. Sorry. Yeah. Or so we are left with only one step, nothing but remaining nodes in the queue are centers actually, one or two nodes, right? So we have to collect them and we have to return it, right? So I'll just go with list. Let me go with integer here. Answer equals new array list. So this is fine. Yep. So I'll just go with the while loop here. So this one not of leaves dot is empty. This is fine. And answer dot add. So this one, I'll just go with the leaves dot remove. Yep, leaves dot remove. Yep. So the final step is we have to return the answer. We have to return the answer, meaning we have to return the centers actually. So here MHT root, right? So minimum height, uh, this one minimum height tree root actually. So this is it for the code. Let me format the code once and let me hit the run button. I hope this works actually. This has to, let's see. Yep, the sample test cases are getting passed. So let me hit the submit button quickly. Hope this works for all the test cases. Yeah, all the test cases are getting passed. So whatever the code that we have written works absolutely correct for all the test cases, right? I hope the solution part is completely clear along with the approach and the complexities part. So this is pure topological sorting, right? So this is pure topological sorting with the BFS actually. Yep. So we are making use of the queue, right? So this is fine. So yeah, for now, this is it. Thanks for watching, guys.